preparation, but I want to tell one story and make one suggestion having to do with the preparation of cathodes and things that we learned at NRL. I retired from NRL less than a year ago, so I still have a lot of information there. But when we started our heat producing program in 2009, we said, well, you have to get control of the palladium metallurgy, right? And so David Kneiss, I remember him being very frustrated. You get this lot of palladium, and you make 10 cathodes, and you do it what you think is identically every single time, which was the ENEA procedure, where you roll it, you anneal it, you etch it, and you run it. And not one of those, all 10 cathodes had totally different morphologies, even though you thought you did the same thing every time and the material was from the same lot. So we went to the metallurgist. I remember sitting there with Dr. Rath and Imam and said, look, what's going on here? I said, well, what's the composition? When we told him what we thought the composition was, and parts per million, maybe at most 50 parts per million or something. So, well, that has no effect on the metallurgy whatsoever. And so I said, well, okay, then what's going on? And after a while, I thought, well, here is a speculation, but I think an informed speculation about what the problem is with that material. Years ago, I actually discovered transient enhanced annealing in silicon, and ion-damaged silicon, but wasn't smart enough to call it that, so I didn't really get credit for it. But if you ion bombard silicon, amorphize it at the interface between the amorphous material and the crystalline material, you have a lot of damaged but still crystalline material. And it's normally thought when you anneal that damage out of silicon, you have to go to, say, 600 degrees to anneal it out. But we found that at 250 or 300 degrees, that region in the interface annealed out very rapidly. And it was later on realized that that was a limitation in the lateral resolution of an ion-implanted dopant, because that damage annealed out quickly, and those defects in their annihilation transported the dopant laterally a long way. Okay. Then what we didn't know to tell the metallurgists at the time was that when these are rolled, often 1 millimeter palladium is rolled down to 100 microns, or maybe even 50 microns in one roll. Now that is elongations of thousands percent or something. And when you look in the literature in metallurgy, when people study elongations, it's 2, 3, maybe 10% or something to see what the structure does and what it does. So you really are starting out, when you anneal this, at extremely high defective material. And what we also found out later on, which is, and this slide was given by David Kidwell, and I'm just going to reiterate what's on this slide. But there's zirconium. In the newer material, there's zirconium, for example, sometimes up to 10, 20, 30 parts per million. Now, a speculation is that in this highly defective material, when you ramp up the anneal, that zirconium will transient enhance transport and go to the grain boundaries in some kind of stochastic way, and will just pin the grain boundaries and just give you kind of random morphology when you finish and you etch the material. So as a result of that, David went and Jinghao went, and they tried to do a tedious thing of every 5 or 10% to finally get down, and never found that made any difference. So this is a caveat. I really believe in the talk that Vittorio gave, that he's onto something with that morphology. We at NRL have found and defined morphology similar to what he was describing, and we have sent our samples to him for these power spectral density measurements, that you do want that morphology. So all along, the goal was to produce that morphology reproducibly so that we could enhance our chances of getting heat. But this is an open problem that there may be various ways to solve, but it would challenge the one challenge to the research group is how do I prepare these foils reproducibly with the right morphology. That was kind of pictorial. So I want to tell you that story, that it's not really easy. Now what NRL did, Knies company, started making their own alloys, so trying to take different palladium that might not have zirconium in it and make the alloys. And it's very simple. You can do it with a hydrogen-oxygen torch. That's what Jingha did, where you take the palladium, you add some ruthenium or whatever you want, you heat it up in an ingot, you roll it, and you heat it up again to homogenize it. And actually they started working when you add ruthenium into the palladium. But that's one way to inexpensively go after it. So that's a note of caution, I would suppose. Now this view graph that David showed, and I have to get to the tutorial because I don't quite agree with what the impurities were in his lots, but and I think this refers to the older lots, and he was not referring to the older lots. But it was realized right around 2010 at ENEA when Mike and David Knies and Victoria were going over data that the older lots had rhodium and platinum in them, about 50 parts per million rhodium, up to 200 parts per million platinum. And the newer lots had zirconium, yttrium, and hafnium. That's where the zirconium is. All of these are pin grain boundaries. And likely the change was due to switching from aluminum to zirconium boats to do this. It's speculated that prices, they then wanted to get that palladium and rhodium out of the material and resell it, so that's why they changed the process. So, so one of the goals, which we are going to do at Skinner actually, is start making more alloys, trying to get back to this kind of impurity makeup in the material. So anyway, that's a rationalization for what might be occurring and why this morphology is so difficult to get in the material. So that was one comment. The other one is that I had a nice talk last night with Martin and Ed from Aerospace Corporation. And one thing that's been lacking, hugely lacking, in terms of materials analysis in this field is TEM. It's probably not surprising because at NRL it's costing us $2 or $3K per sample, and it's expensive. And at Aerospace they were offering to maybe help us a little bit with some of their analytical techniques, one of which is TEM. And I've heard many people say, well, look, what's important in these materials is the defects. Well, TEM can't find point defects unless you have an aberration-corrected material. But you can find some of the extended defects, which everyone talks about. They want dislocations, they want extended vacancy clusters and interstitial clusters and all that. The TEM could find that. So I really think we should take maybe what Vittorio showed here. He showed one that produced heat and one didn't. It's a very nice systematic study. We maybe take pieces of those, do some TEM, and do we see these defective materials that in the ones that work, a lot of defects in the ones that work, and not so much defects in the ones that don't. That's the suggestion as a way forward. So I think that's all the time I need. I wanted to tell that story, that the palladium metallurgy isn't easy, and that we ought to put in some new techniques to go after. Many models say you've got to have defects. Well, let's find the darn things. Okay, thank you.